Hi, in this video I'm going to discuss about section 9.7 from the book. Okay guys, so the 9.7 is the Taylor's polynomial and approximation. So we have seen so many types of functions, right? Polynomial function like x squared, x cubed, 5x squared plus 7, like that type of function. Also we have seen trig functions, sine x, cosine x, tangent x, like that. Also we have seen rational functions, meaning that you have a function on the top, it is a ratio of the two functions. You have seen logarithmic function, you have seen exponential function, and so on. Okay, but we can approximate all those non-polynomial functions like rational functions or trig functions, log function, exponential function, or hyperbolic functions. Any of those type of functions, we can approximate those functions at a point by a polynomial function. Okay, so what that means is, for example, if you have suppose you have a weird type of graph of a function like that, right? But we can approximate for this function at a point C, we can approximate that the function, the value of the function at C by a line we call linear approximation, right? You see that around the point C, the value of the function, that green curve, and then the black curve, the black line, are almost the same around C. So you can approximate. This is a linear approximation. You have seen that in Calc 1, okay? But if you want to use a quadratic approximation, so you can get a function, right? You can get a function that shows similar behavior around the point C. So you see that the pink curve or the red curve is giving a better approximation around C, right? So this is the linear approximation. This is a quadratic approximation. You can do cubic, you can do biquadratic, and any degree approximation. We can find a function, polynomial function of any degree, to approximate a complicated function, okay, around a point x equals to C. Okay, so the one is the one very well known and famous method is the Taylor's polynomial. If you have any type of function and if you want to know what is the polynomial function that is approximately same to the given function, okay, at a point x equals to C, the Taylor's polynomial is let fx has an derivative at x equals to C. Okay, then Pnx, it's a polynomial function of n degree of x. To approximate fx is given by f at C, that point C, functional value, and then x minus C times f prime of x, the first derivative, plus x minus C squared times f double prime at C divided by 2 factorial, plus x minus C to the n times the nth derivative of fx at C divided by n factorial. It is called Taylor's polynomial of f at x equals to C. Okay, if you take C equals to 0, this equation, that equation become Pnx equals to C is replaced by 0, f0 plus x minus 0 is x times f prime at 0 plus x squared times f double prime of 0 divided by 2 factorial, plus x to the n times f, the nth derivative of f at x equals 0 divided by n factorial. Okay, it is also called the Maclaurin's polynomial. Okay, all right, let us see some example. All right, let us see an example where you want to find out p1, p2, p3, p4, p5 for fx equals to e to the x at x equals to 0, meaning that around the origin, around the when x equals to 0, you want to approximate, you want to find a polynomial function that is almost same, that has almost same values as fx equals to e to the x. Okay, you see that when there is a subscript n, p sub n x, then you go up to nth factorial, right? You see that when there is nx, then you go up to nth factorial, right, in the Maclaurin series as well. Since x equals 0, you want to find out Maclaurin series of degree 1, degree 2, degree 3, and so on. Okay, so how do you do that? Is basically what you do here is find out p1x. It will go up to what? F at 0 because c equals 0. Okay, and then plus x is x, and then f prime at 0. But what is our fx? Our fx is equals to e to the x, right? What will be f prime of x then? F prime of x is also e to the x, right? Now you plug in 0 for x. What do you get? You get f at 0 is e to the 0, that is 1, and f prime at 0 is also e to the 0, that is also 1. So what do you get basically? Basically you get that as 1 plus just x. So p1x is 1 plus x, because you just plug in here, right? That's what you did, right? You plug in there. Now what if you want to do p2x, then you need to go to second derivative. If you do that, p2x is equals to, the formula is f at 0 plus x times f prime of 0 plus x squared over 2 factorial times f double prime of 0. You see that? F double prime of 0. Okay, so what you need to do, you have found the fx equals to, fx is e to the x, f prime of x you found as e to the x again. What is f double prime of x? This is also e to the x. Now if you plug in 0 for x, you get that is also 1 again. So if you do that, then you get 1 plus x squared over 2 factorial. Okay, similarly if you find out p3x, it will be 1 plus x squared over 2 factorial plus, and then x cubed over 3 factorial. Okay, similarly p4x will be 1 plus x squared over 2 factorial. You need to go to fourth derivative, right? X cubed over 3 factorial. That's what you got. One more term, two more terms after this in that formula, right? And then plus x to the 4 over 4 factorial. That's what you get. Okay, and then p5x is 1. You need to go to fifth derivative, up to fifth derivative. X plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5 over 5 factorial. That's what you get. Okay, guys. So so this is how you find out the Maclaurin series or the Taylor series, because if the c is 0, then we call Maclaurin's, otherwise it is the Taylor series. So Maclaurin series is the special case of the Taylor's series, right? So what do you get from here? Then let's do another example. Find p4x and p6x for fx equals to sine x at c equals to pi over 6. So you want to find out at c equals to pi over 6. Okay, guys. So how do I do that? Let us do that. So what is fx? Let us write down that. What is fx? F of x. Since we need to find out p6x and p4x, we need to find out up to 6th derivative. So fx equals to sine x, right? What is f prime? Is cosine of x, right? What is f double prime? Is negative sine x. F triple prime is equals to negative cosine of x. Fiv is equals to the fourth derivative, so that will be sine x again. Fv, fifth derivative, is equals to cosine of x, and then fvi, sixth derivative, is equals to what? That will be negative sine x. You see that? Now what do you get? So you need to find out, because the formula says that you need to find out at x equals to c, f prime at x equals to e, f at x equals to e, f double prime, like that. So what is f of pi over 6? You plug in that. That is 1/2, right? What is cosine of pi over 6? So f prime at that time will be root 3 over 2. F double prime at that time, that is negative 1/2. Okay, f triple prime equals to negative root 3 over 2. That is negative. Okay, negative root 3 over 2. All right. And then f, the fourth derivative term will be again 1/2. Fifth derivative term will be root 3 over 2. And then sixth derivative term. So the sixth derivative term is fvi. It is negative 1/2. Let us find out p4x. What is p4x? P4x is equals to, so the formula is fc okay, plus x minus c times f prime of c plus x minus c squared times f double prime of c over 2 factorial plus x minus c to the, so that will be x minus c to the cube times f triple prime of c over 3 factorial plus x minus c to the fourth times f iv fourth derivative at c divided by 4 factorial. Okay, so that is the p4x, right? Because you need to go to up to iv or fourth derivative. So what do you get? You get 1/2 plus what is x minus c? X minus c is x minus, let me write down what is f prime of c, root 3 over 2. Let me write down that root 3 over 2 times x minus pi over 6. That's what you get. Okay, and then plus what is f double prime? That is negative 1/2. Let me write down negative sign. Negative 1/2 is that, and then there is 2 factorial, right? What do you get? So basically 1 over 2 times 2 factorial at the bottom, right? Times x minus pi over 6 square. That is the second one. The third term. Plus the fourth term will be, what is the f triple prime? That is negative root 3 over 2, right? So you can write negative root 3 over 2 times, that is 3 factorial. You see that? And then what is x minus c? That is x minus pi over 6 to the cubed. And then what is the next? Plus, that is a fourth derivative. What is the fourth derivative? 1/2 again. 1/2 times 4 factorial, because this quantity is 1/2 and divided by 4 factorial is still there. So that's why I wrote 4 factorial. And then what? Then times x minus pi over 6 to the fourth. Okay, that is the end. Similarly, if you want to find out p6x, so you will have all these p4x term, and then plus you will have 2 more terms, right? How that look like? So fifth derivative will be 1/2. Fifth derivative is root 3 over 2. Root 3 over 2 times 5 factorial, right? That's what it looks like. And then x minus pi over 6 to the 5, and then plus the 6 will be, that will be minus, okay, minus 1/2, and then 6 factorial in the denominator times, and then x minus pi over 6 to the 6. So that is basically the p6. Okay guys, so this is how you find out the Taylor's polynomial. Okay, so you see that whenever you take the bigger degree of the polynomial, like you see that if you draw the graph of e to the x around x equals to 0, okay, so this p1x approximate just okay, p2x approximate better, p3x, when you increase the degree of the Taylor's polynomial, you will get better approximation around that point. Okay, so if you have a lower degree polynomial, then you will have just okay approximation. But the increasing the degree of the Taylor's polynomial basically increases the accuracy of the approximation. Okay guys, let us see one more example that how we use the Taylor's polynomial, or how we use the Maclaurin's polynomial to find the value of a function at a point. Okay, as I mentioned earlier, what I showed you is I had created a graph. For example, suppose that you want to know that, let's suppose that there is a graph, like very complicated type of graph, for example. Okay, and suppose you want to find the height of the function at x equals to 2 of that graph. So how can you do that? Is you try to find out the Taylor's polynomial that approximate this graph around that x equals to 2. Okay, suppose that if you use the linear polynomial, or if you use p1x to approximate this at x equals 2, this is what you will get. This is the linear approximation you are getting, right? Now if you want to find the value of the function fx at x equals to 2.1, let's say, for example, suppose you want to find out f at 2.1. In that case, what do? You find out the approximated polynomial, Taylor's polynomial, that is p1x, and then you plug in x equals to 2.1 there, on this black curve. Okay, so because the height of the black line and the height of the red line or the pink line are similar, so you use that Taylor's polynomial to approximate the height of that red function fx around that point, because the Taylor's polynomial p1x approximates the function around 2. If you use p2x though, p2x, then it will be a quadratic approximation, right? So it will look like the second degree approximation polynomial look like this. This is p1x, this is p2x. In that case, you will see more accurate values around 2, okay, because this blue curve and then the red curve overlap in more region, in more interval than in p1, than with p1. Okay, that's the idea what we're doing here. All right, so on this example, what I'm going to do here is, the question is, for fx equals to natural log of x, use p4x to approximate f at 0.99. Okay, so since 0.99 is near x equals to 1, okay, so what we'll do is we'll try to find out the Taylor's polynomial around x equals to 1 for this function, okay, and then we will plug in that value. Okay, we will plug in that value there. All right, guys, so first of all, what we will do here is basically, all right, so let us write down what is f of x here. So f of x is natural log of x, right? What is f prime of x? You need to go to up to fourth derivative, because p4x, right? What is 1 over x? What is f double prime of x? That is negative 1 over x squared, right? Because if you move this to the top, you will get x to the negative 1, and then you use the power rule, right? F triple prime of x is, you get 2 over x cubed, and then f fourth derivative of x, it is basically negative 6 over x to the fourth. Okay, that's what you get. All right, because you know how to find out the third derivative. You move this to the top, it is negative 2 times, so negative 1 times negative 2 times x to the negative 3, and you will get 2 over x cubed, and this will be negative 6 times x to the negative 4, that is negative 6 over x to the 4. That's what you get. Now what we want to do is we want to find out at x equals to 1. Why? Because our goal is, we want to find out, our goal is finding the value of f at 0.99, right? But 0.99 is close to 1. Okay, let us find out approximated polynomial at 1. Okay, so at x equals to 1, which is c, right? F at 1 is equals to what? You get 0, and f prime at 1 is equals to 1, f double prime at 1 is equals to negative 1, f triple prime at 1 is equals to 2, f fourth derivative at 1 is equals to negative 6. Okay, so the p4, the Taylor's polynomial p4 is f at 1. What is f at 1? Is 0. F, let's write down that f at 1 plus x minus 1 times f prime at 1 plus x minus 1 squared times f double prime of 1 over 1 factorial, sorry, f double prime of 1 over 2 factorial, because whatever the derivative is there, that factorial is there. Okay, x minus 1 to the cubed, okay, times f triple prime at 1 over 3 factorial plus x minus 1 to the fourth times f iv at 1, that is fourth derivative, over 4 factorial. That's what you get, right? So what is f at 1? 0, right? Plus x, so this is p4x. Okay, that's p4x, and then x minus 1 times, this is 1, right? So that value is 1. So plus x minus 1 squared times, what is f double prime of 1? Negative 1, right? Negative 1 over 2. So this is what you can write. So you can write that as negative, okay, so you can write that as negative 1 over 2 factorial is 2, plus x minus 1 to the cubed, x minus 1 to the cubed times f triple prime of 1, that is 2 over 3 factorial is 2 over 6, 3 factorial is 6, plus x minus 1 to the 4 times f fourth derivative at 1 is negative 6 over 4 factorial is 4 times 3 times 2 times 24, right? So what you get basically is p4x is equals to x minus 1 minus x minus 1 squared over 2, right? And then plus x minus 1 to the cubed over 3. You see that? Because 1/3, 2 6 is 1/3, plus x, minus, because there is minus there, right? So minus x minus 1 to the 4 divided by 4. Okay, so this is the 4th degree polynomial approximation of natural log of x around x equals to 1. Okay, this is around x equals to 1. This is the polynomial approximation for natural log of x, okay. Now, so our goal is to find out f at 0.99x. What is happening there is, suppose the natural log of x, okay, natural log of x has the graph like this, okay, natural log of x has a graph like this. All right, now this is 1. At 1, the value of the natural log of x is 0. This is the real, this is the basically the exact graph of natural log of x. But you want to find out that the approximate the value at negative positive 0.99 at that point. Now what we did is we first find the equation 4th degree approximation of this natural log of x. Maybe suppose that the 4th degree approximation is like that, something similar to that. Okay, now instead of finding the height of that red curve, we are finding the height of the p4x. Okay, right there. So what I'm going to do here next is I want to find out p4 at 0.99. Okay, instead of plugging in at natural log of x, I'm just plugging in into this approximated function. And if you do that, what do you get? You get 0.99 minus 1 is negative 0.01. You see that? Minus negative 0.01 square divided by 2 plus negative 0.01 to the cube, because x is 0.99. 0.99 minus 1, okay, that is negative 0.01 over 3, and then minus negative 0.01 to the 4 over 4. Okay, so let us use calculator for that. So if you use calculator for that one, you will get so basically you got negative 0.01 and then minus 0.01 square divided by 2, and then again minus 0.01 to the cubed divided by 3. So divide by 3, and then the last one will be minus again, because negative 0.01 to the 4th will be positive 0.01 to the 4th. So 0.01 to the 4th, okay, and then divide by 4. That's what I got. So the value I got here is, so that is negative. So negative 0.01. That's what I got. Negative 0.01. That's what I got. Okay. Now, what is the exact value at what is natural log of 0.99? Let's find out that. So the natural log of 0.99 is basically negative 0.01. So basically, let me write. So the value of p4.99 is negative 0.01005 and then 3003. That's so many decimals. And if I find out this directly using calculator, what do I get? I got negative 0.01005 and then 0.3. You see that how many decimal places are the same here? So 1 2 3 4 5 6, up to 6 decimal place. You see, p4 was able to approximate up to the 6 decimal places. Okay, so you get exactly the same value up to 6 decimal places. So basically p4 was doing good job on approximating the value of natural log of x at 0.99. So we use Taylor's polynomial of degree 4 around x equals to 1, because 0.99 was around x close to x equals to 1. Okay guys, so this is how we use the Taylor's polynomial to find the value of a function, around a point. All right, thank you.